for the rest of this proof, I needed to make my x-axis even longer, and I needed to draw the entire circle P. Remember, P was the orange circle whose center was somewhere. So center was somewhere here, x0, 0 on the x-axis. And I wanted to rephrase again what we're trying to show. We're trying to show that the hyperbolic distance from any point on Q to A is the same number. That will show that Q is a hyperbolic circle. If the distance from any point on Q to its alleged center is the same number, then that means it is a circle. And I'm telling you exactly what the number is. It's the distance from A to C. So what's the any point? Well, that's the point E, right? So I drew any geodesic, any circle P that intersected the circle Q at some point E. So i.e. want DH E A to be DH AC. So this E represents here this arbitrary point on Q. Okay, so what we're going to do is the following now. I'm going to draw yet another circle. That circle is called N, and that's going to be a circle that is centered at this point of intersection here, G, of P and the x-axis, and it should pass through A. So first of all, let's define G. So let G be a point of intersection of P with the x-axis. Okay, and then I'm defining N, so let N be the circle centered at G passing through A. Well, but it's centered on the x-axis, so if it passes through A, it also passes through A prime. So also through A prime. And I'm going to be considering the inversion with respect to that circle N. Yes, yet another inversion. So I want to note some things about this inversion. Several things. One, note that this red circle, so this is the N, right? That's the red circle, N. Of course, it's bigger than the orange one because the orange one extends from here to there, and G is just the center of the red circle, so that's even bigger. But it is just another circle centered at the origin that passes through A. And we proved that if I take the inversion with respect to P, the orange circle, of Q, I get Q back. But P was an arbitrary circle, so I can just as well use, in that same proposition, I could have used the circle N, and I would have gotten the same answer, right? So I want to know that In of Q is still Q, right? Because the proposition essentially said, take any circle centered on the x-axis that passes through A, and then the inversion with respect to that circle of the circle Q is the Q back. So I'm applying this proposition again, but this time for N. So this is by proposition. So that's one thing to note. What's second thing to note? 2. In of the circle P is a line. Why is that? Because of the choice of that circle N. Note, G is the center of the circle N. And I'm taking the inversion with respect to N. So the circle P, the orange circle, passes through the center of inversion. And what do we know from the theory of inversions is that the image of a circle that passes through the center of inversion, of the circle of inversion, is a line. Any circle that passes through the center of inversion is mapped to a line. P passes through G, which is the center of the circle N. So In of P is a line. What line? How many points determine a line? 2 points determine a line. So 3. Note that, of course, In fixes A, because A lies on N. That's how it shows N. And A prime also lies on N. So it also fixes A prime. So as any 2 points determine a line, we get by 2 and 3 that the image of P is the y-axis. It's the line that passes through A and A prime. Okay, what else do we know? I would like to know what happens to this arc, AE. So I already know that In of A is equal to A. The question, what is In of E? So I want some characterization of E. So let me erase this. In fact, I don't think I need this part anymore. It's just that the image is the y-axis, so I can erase this. So what is In of E? So let's characterize the point E a little. So E is the intersection of the circle P with the circle Q. So its image should be the intersection of the image of P with the image of Q. But I now know what these things are, because we observed in part 1, which I unfortunately erased, that was part 1, that this is actually Q. And we also know what In of P is, that's the y-axis. So this is pi 1. And this is the y-axis. So the image of E is the intersection of the y-axis with the circle Q. So that's the point C. So In of E is C. But N is a circle centered at the x-axis. So the inversion with respect to N is a rigid motion. I don't need this part of the picture anymore, as N is centered at on the x-axis, we know that inversion with respect to N is a rigid motion. That much we know from the video about rigid motions on the hyperbolic plane. But so what does that mean? So it preserves distances. In other words, the distance between the points A, the hyperbolic distance, it's a hyperbolic rigid motion, right? The hyperbolic distance between the points A and E is equal to the hyperbolic distance between in of A and in of E. But what is in of A? That's A. And what's in of E? That is C, which is exactly what we wanted. So the hyperbolic distance between A and E is equal to the hyperbolic distance from A to C. Now imagine take some other point on Q, right here, and repeat the same thing, that is draw a circle that passes through both A and that point and is centered on the x-axis, and you'll get another sort of ray like this. And this whole argument, because E was arbitrary, again proves that the distance from this point to A is the same as the distance from A to C. So the hyperbolic distance of all these points here from A is equal to the distance, hyperbolic distance from A to C, right? Note, why am I taking these arcs? Because these arcs, if I have these points like A and E that are not vertically aligned, then how do I measure the distance between them? I have to draw a geodesic between them. And what are the geodesics between two points that are not vertically aligned? They are circles centered on the x-axis that go through these 2 points. Okay? That's why if I want this point and that point, for example, how do I know what's the distance between them? Well, I have to look for a circle that is centered on the x-axis that goes through these two. And then the distance is the length of that curve. But, so I know that this length is always equal to the distance from A to C, so it's constant. So this proves that all the points on Q have the same hyperbolic distance from A as the point C does. So they all have the same distance from A. In other words, Q is a circle, a hyperbolic circle.